Unfortunately, my pointer is not quite working. I can still point to things, but I need to turn pages like this. Okay. All right. I think I don't need to tell you now this that deep learning is super successful. We have seen a lot of academic breakthroughs, and we have seen a lot of commercial miracles. And also, I don't need to tell you that robustness issue is everywhere. They range from image problems to other domains like NLP domain, and it doesn't matter whether your model is small or large, because even for foundation models, people actually found there are still robustness issues. And actually, if we step back, robustness issue is only one of the many pieces of the terms people use in trustworthy AI, right? When people say trustworthiness, of course, there's a lot of terms, and also there's a lot of disagreements what this thing exactly is about. But you can roughly call these terms, and I mean, more or less, these are what people are talking about. And of course, moving to large language models nowadays, there are some new concerns. For example, you can interact with large language model in multiple rounds. So that create a lot of new possibilities that you can break up, right? So it's clear now that this kind of trustworthy issue and safety to some extent is international concern, and we are seeing a lot of international policies or regulations, or at least government start to think about this kind of policy or regulations. So that's one thing that's clearly happening in AI community. And on the other hand, we know that a modern AI or modern deep learning is supported by three key pillars, right? One is data, one is GPU or any specialized computing hardware, and the other is algorithm. And algorithm side, I think that's really flat, right? Everybody have access to archive, we can read a lot of papers. GPU side, that's not fair, of course. As academic, we never can compete with industry labs in terms of GPUs or TPUs we have. But I want to stress another point today is about data. Because if you look at the fields where the modern deep learning are super successful, there are only two domains. One domain is computer vision, where you have this open source data set. The largest one is 5 billion. I think it's 5 billion images, even with some caption, text caption alongside with the images. And NLP domain, the largest, the public data set, you have terabytes of NLP data. That's a lot. I mean, you don't compare NLP data with images, right? 1.6 terabytes, that's really a lot in NLP domain. And actually, if you watch the news, there's some interesting news about OpenAI. I think this year, OpenAI, they tried to use some pirate books from this famous website called Library Genesis. I don't know, probably most of you know what Library Genesis is, right? So they are using these kind of books to train their language models. So that's something that's discovered, or that's actually released by some of their former employees to the public. But well, anyway, I'm not complaining about the copyright things. I mean, that's a complicated issue. But I'm just talking about they have huge amount of data, really huge amount of data. That's probably all the data, language data we have ever collect over human history, right? But besides these two domains, think about any other domains, like for example, scientific domains. If you talk to any scientists that are working in particular scientific domain, they always tell you that, okay, our data are sparse, right? That's a term they use a lot, sparsity. And medical domain, for example, I work with medical doctors a lot. There are a lot of reasons why they don't have a whole lot of data. Either their diseases are rare. I mean, like for example, I ever work on a project where over 40 years, the University of Minnesota hospital, they only collect like 400 cases, 40 years. So these are rare diseases. You can't do much about it. And other situations like, okay, the hospitals, they don't want to share the data with outside. For all kind of reasons, privacy reasons, and also commercial calculations. That's an important thing. So back to 2019, DOE already released this technical report or white paper about the big problems in scientific machine learning. So actually, one out of the six important directions they point out is actually to how to integrate scientific knowledge into AI models. Okay. But if we think about learning theory itself, obviously we know that there's no free lunch, right? We think about all kinds of ways trying to break the dimension crisis, right? When you go to high dimensional space, we know that we need exponential many samples. Right? So unless you can assume something about the function, right? That's all the kind of things we play with, right? As machine learning researcher or as data science researcher or whatever in general. And I think in the past 1 decade, we have been mostly in this low-hanging fruit regime where we have huge amount of data. I'm talking about mostly here in the computer vision domain. We do a lot of crazy things, train foundation models, train large-scale generative models, right? But it's becoming less and less so if you move to any downstream X domain where you really want to push AI into. I'm talking about like physical science or medicine or you all of a sudden you realize you have limited amount of data always, and also of course you have a lot of domain knowledge that you probably want to integrate into your framework. So that's another thing I want to highlight. It seems like AI plus knowledge, that kind of integration is becoming more and more necessary and also imperative. So today's talk, I'm going to just share several very quick stories. My talk tends to be very broad, but not very deep. If you want some depth, you can read the papers I refer to, but I just want to tell some high-level stories so that you appreciate what I care about. All right, so the first thing, come back to the robustness issue I talked about. So in order to talk about robustness issue, actually the first thing is that we need to be able to evaluate robustness. Right. So how people nowadays evaluate robustness? I'll just take computer vision as an example. So what they do typically is that they'll collect a reasonable sized test data set, for example, 10,000 images from image match. Okay, so these are test images. For each of the image, I'll try to find the worst case perturbation within a budget. Okay, that hopefully can break my AI system by solving this outlier problem. So I try to find the worst case loss subject to some perturbation budget, and also I want to make sure that the perturbation remain a valid image. There are some words, but I'm not going to talk too much about the mess. But this is what people do. Typically after you find this kind of worst case perturbation for each image, and then you evaluate the accuracy, which is called robust accuracy. And then you report that, and then you compare that with the accuracy before you inject the perturbation, right? Obviously, the higher the better, but typically you'll see some gap, some substantial gap actually. Now the problem here, the central problem here is actually a computational problem. If you look at these mathematical formulations, we typically would have non-convex losses. And often we could also have non-convex constraints. So D here means distance, which basically defines the budget, perturbation budget. You can define all kinds of distances, although computer vision domain is arguing that the typical LP norm doesn't work because they are not physically meaningful. They want to move to some more complicated distances. And that actually makes this function highly nonlinear typically. And similarly for the second formulation, again, this one is slightly more complicated. I don't want to stress too much, but you can see the complication here. There's some highly nonlinear non-convex constraints and some nonlinear and non-convex objective. So how well you can do the robustness evaluation depends on how well you can solve these operating problems. That's very clear. Okay. Now, what people are doing in practice? Well, for I'll just take this first one as an example where you try to find the worst population. Typically, people will choose very simple distance, like L1, L2, L infinity. These are very common choices. And then they run something called gradient descent, projected gradient descent. In case you haven't heard of this, basically, we just take gradient stuff on the objective, and then after each step, we project onto the feasible set. Okay, so that's what they did. And I want to say that a couple of important parameters or hyperparameters for this algorithm. One is obviously the step size, and another one is in total how many steps you want to run. Okay. And of course, the real algorithm that people are using in state-of-the-art robust evaluation package is much more complicated than this one. They have all kind of heuristic building. I'm not going to talk about that, but basically behind the scene, this is still the soul of the algorithm. Okay. Now, I want to focus on the empirical aspect because you can take this state-of-the-art robust evaluation package and just use that default parameter. This will set like a number information to be 100 for no reason. But anyway, if you run that, and in our evaluation, we basically run very long time. We run like 10,000 iterations, and we just try to see what's the quality they actually get if they stop at 100 iteration. And it seems very, very clear that often, very, very often, actually they stop very prematurely. Now, what that means? Well, what that means is that, okay, so maybe my model is not very robust, but your evaluation algorithm, because you stop early, it's like you kind of weaken the attack, the strength of the attack. And so you didn't find a successful attack, and then you claim the model is robust, right? It's like your algorithm actually weaken that modeling. And this happens often, I can tell you. What we found is that this probably happens 80% of time. And so what this means is that if you use this toolbox to do robust evaluation for deep learning models, they tend to be overly optimistic. And it's actually very, very overly. Okay. Now, if you take some more complicated distances, as I said, computer vision community and actually machine learning community is also pushing this. They argue that, okay, the LP distance probably doesn't correspond to the actual population we see in real world, right? Let's try to get some more complicated modeling by changing the distance metric. So one thing that in the past few years that people are pushing is called something called perceptual distance. So what that means is when I try to measure distance here, I pass them through a pre-trained neural network, and then I compare the distance, I calculate distance in the feature space. That makes a lot of sense, right? If we think feature abstraction makes a lot of sense. So that would turn this constraint into a highly non-convex and nonlinear constraint, so they can't do projection anymore. Now, what they do some method called parenting method. I think some of you probably have that kind of background, operation background. You know what parenting method is. So basically, it's a method that if you see some violation, you try to penalize that in the objective, right? But they are doing the most naive way of parenting method, which from an operation point of view is known to be very bad at finding feasible solution for you. So what that means is that after they solve this, they are actually not finding an X prime that actually satisfy these constraints. Then how can you trust your robust evaluation, right? Because your modeling is saying, okay, so we allow this amount of budget, and then I'm trying to find the worst case attack based on this, but the numerical operation method is actually not doing that. They didn't find a point that actually satisfy this budget. So I don't know, maybe it will be overly pessimistic, or maybe it will be overly optimistic. But anyway, we found in majority cases we evaluate on that happens. So they are finding some substantially infeasible solutions for the problem. So I'm going to skip some of the numerics. So the high-level message I want to deliver is that although a lot of people are talking about robustness, and also you can see a lot of open source package out there, just don't trust them. That's the only message I can tell you. Don't trust them. They are not trustable. So just to summarize what I said, why they are not trustable? Because they are not very careful in solving these operating problems. Because when you say you solve an operating problem, there are several things we care about. If the problem is totally smooth, for example, we care about at least they should find a stationary point, right? Even if they are not doing global operation. They didn't do that. And for constraint problem, at least you want to check you find something that's numerically feasible. They didn't do that. And of course, practically you probably also care about speed. That's why, projected gradient method, they are not patient and they just said 100 iteration as budget, but end of the day, it turns out that they found something infeasible. So now if we step back and think about this operating problem, these are just the generic nonlinear programming problems, of course, with constraints. There are a lot of solvers. There are a lot of commercial solvers even for these kind of problems. But they have all kind of limitations because typically they are built for small scale problem, right? Typically, yes, and also typically they can't handle non-smooth problems, or their behavior on non-smooth problem could be very unpredictable. Okay, so that's what I know at least. So when I encounter this whole issue about robustness evaluation, I started to think about a particular package like Granso. So this package is built by several operation folks. I think maybe some of you would know Mike Overton, who's a very famous numerical analyst in Crown Institute. So what they did is for non-smooth problem, they actually modify a classical numerical method called sequential quadratic programming. Okay, but traditional sequential programming is actually smooth problems. But again, for deep learning, we may face non-smooth problems. And they did a little bit modification. They did some modification about the lineage search process, and also how would you check for stationarity. Again, I'm not going to get into the details, but anyway, so they make some necessary changes so that they can work relatively reliably for non-smooth problems also. Okay, so this is a MATLAB package basically with principled line search and stationarity and feasibility check. Okay. But of course, the only problem with this is in doing deep learning, we typically are dealing with PyTorch or TensorFlow, right? We are not playing with MATLAB. So our work here is very humble. Basically, what we do is that we translate this whole package into PyTorch. Okay, we didn't invent anything new. We basically just spend several months try to translate everything and try to take advantage of PyTorch features and really make it work with generic non-smooth, non-linear programming problems, and especially be compatible with PyTorch. Okay. And so far, I believe this is actually the first general purpose numerical package for solving hard constrained deep learning problem. Okay, so that's something I'm more proud of. Again, I'm not saying we invent this package. We are translating the MATLAB word into PyTorch, but I can see that that actually help us a lot in several applications. For example, one thing, get back to the robustness evaluation. Actually, before I talk about the general things, that we on top of that package called PyGranso, we actually have some additional tricks that we try to speed up things. But again, I'm not going to get into this kind of details. So end of the day, what we get is this: the state-of-art package for robustness evaluation. They actually only works for L2 norm and L infinity norm. And with the new package we have, we can actually work with any differentiable, actually almost everywhere differentiable kind of metrics. That means it could be LP norm, could be neural network distance or whatever. Basically, any reasonable distance you can think of, so long as it's not like a discrete kind of distance. Okay. And also our package actually, when you run the package and try to verify or try to check robustness, it gives you an indication about how well you are solving the problem, because we are doing rigorous feasibility and execution check. Okay. And just want to give you a quick example for the one that use perceptual distance. So it's a heuristic method, inexact, I think it's an inexact penalty method. So you can see that their method actually is about 70% of the time they don't find a feasible solution at all. So then that means whatever they report about attack success, that's meaningless. With our method, this one is our method. I mean, this is still a small percentage evaluation, but at least if the solution violated the constraint will tell you it actually violated the constraint. Okay, so we get some result that's much more useful for robustness evaluation. So if you are interested in this, you are welcome to check out this paper. And also the package is released on GitHub. So just want to tell you a little bit more about this package we are developing called PyGranso, and underlying that is a framework called NCVX, which is standard for non-convex. Well, you know CVX, right? What CVX means. So the goal, we are still developing this, by the way. So the goal is that I want to develop this package so that practitioners only need to specify their mathematical problem, especially deep learning related problem, and then they can press the button and they really get a solution quickly. That's my end goal. But of course, it takes many steps. Currently, we have one solver built in, which is called a PyGranso, which is a deterministic solver with a sequential quadratic programming. So the limitation is it's not very scalable yet. We can deal with like up to 5 billion, sorry, not 5 billion, 5 million variables, which is not like crazy for deep neural networks, but still you can already do a lot of things. So I just want to share with you some of the things we do. Robust evaluation, I really talk about that. I also use that to collaborate with people from civil engineering on classical engineering design problem that's called topology optimization. And also I work with the medical side, on the medical side, and work on some of the problems related to data imbalance. And one thing I'm especially proud of is recently we got a fund from NSF. So that's about how do you incorporate physical constraints in material discovery. So that's something I'm very proud of. Basically, there you have a lot of constraints that's basically telling you, this material have higher energy than the other one, and vice versa, this kind of ranking information. But so far in material discovery community, they haven't done this at all. Everybody knows this is useful, but nobody has done this at all. So I believe we are the first doing this. Okay, so let's change the gears a little bit. Now, we talk about robustness. Now we know from statistical learning theory that we can't expect like 100% model all the time, right? The fundamental barrier is the noise in the data, right? We can't do better than the level of data, not level of the noise itself. And I believe similarly, we probably can't solve this robustness issue forever. Probably. I get a feeling, I don't have a rigorous mathematical proof, but I think I talked to a lot of people. I got a lot of similar kind of sentiment that we probably are not going to solve that problem. So what that means is at the end of the day, we have to live with these imperfect models forever, probably. Now, how do we deal with them? Right? Or in other words, do we think the imperfect models can be deployed? So that's actually a question that I'm fascinated a lot about this. I believe so. There are all kind of ways that we can actually try to make AI models to be cooperative with humans. One of the approach is called a selective prediction. I may go with the other names like prediction with some reject option. That's another name for that. By the way, there's another line of research That's doing something slightly different than this one. It's called a conformal prediction. But anyway, so I'm not pursuing conformal prediction, but this one is basically that when you make a prediction, if you feel the prediction is likely to be a mistake, that's just not doing it. Let's just leave that to human expert. Let's just not using AI models for doing that. Okay, so that's the underlying idea. And end of the day, how do you measure performance in this kind of situation? Well, there's a natural trade-off between how many of the prediction you actually keep, which is called a coverage. Okay, let's say we keep half of the most confident predictions, the coverage is 50%. And also the error you made or the average on the part you keep, which is called selection risk. So typically the way that people evaluate this is a trade-off between these two quantities. It could be other quantities. I mean, this one really depends on your application, but practically, of course, we really worry about this region. That means the region where the risk is very low. So just imagine a medical application where the doctors tell you, okay, can you give me a prediction model where the error is below 0.1%? I don't worry about how many patients you actually care about. Don't care about. You actually can help. Maybe your model can actually help with 10% of the patient, but just guarantee your model can do like the error is below 0.1% for the part that you actually make prediction on. So that's why we really care about this region where the risk is very low in order to make these kind of models deployable. Okay. So I think I'm going to just gloss over this part due to the constraint of time. So I know that what this whole thing is about is how do we quantify a certain level or confidence level with predictions. There's been a lot of metrics that people propose, a lot of score functions, so-called. Most of them have to do with softmax output or the softmax logics in predictions. So what we found is that this is actually a very bad choice because it's actually super sensitive to the scaling. And actually, for people who come from statistical background, you may know this notion called calibration. So this have a significant problem there with calibration. But fortunately, it seems like if your goal is really to just reject the unreliable ones, actually, it seems like you don't need to worry about calibration. What you need to worry about is that the confident ones get a higher rank than the lower confident ones. You basically just worry about ranking. So basically, our contribution here is that we propose another very intuitive kind of score function based on the raw logics. That's actually based on the margin, the classic notion of margin. Okay, it's not surprising at all, actually. You basically take the largest logics compared with the second largest and take the difference. That's the indication of confidence. And by the way, this is not our invention. We actually found later that back to 84, the King actually proposed this when he worked on the digit recognition. So, but surprisingly, that disappeared after that paper. People never talk about this anymore. But anyway, so after we proposed this, we dig in the literature, we found the King actually first proposed this. But anyway, so let me move to so on real data evaluation, this is doing just consistently substantial better than other natural confidence score function like a softmax, which is most commonly used. And we are also doing some follow-up work, like, there are tens of different confidence functions. It's hard to say which one is a clear winner on all data set. And, can we actually combine the strengths of them by doing some ensemble learning or something, to get a uniformly better one. So that's something ongoing, and we already get some very positive result actually for this. All right, up to this point, because I'm going to switch the gear to other things. Any questions so far for this part? Yep. algorithm for learning. Which confidence function are you talking about? So this one?
You show select classification. Got it.
F G. Oh, I think you are talking about this setup.
Yeah.
Oh yeah. So
Learning.
F is a given classifier. So we are just assuming the classifier is given as is. We never touch on the classifier at all. It's black box. G is the selector. Yes, we'll do something to design the selector basically. Yes.
You're learning line G.
Yes, exactly.
Yes.
Yes. So again, so the important thing here is the score function. So this S is a score function. So the different papers basically propose different kind of score functions. What we propose here is a very simple one. It's actually the margin based. Basically, it's if you look at raw logits, when I say raw logits, that's the logits before you take the softmax. You compare the first one and the second, the largest one versus the second largest one, and take the difference. And that's the margin. Because this is I think this is in multi-class SVM literature, this is the definition of confidence margin, this one. Actually, it doesn't matter because you can apply this to even for no matter how many layers you have gone through, because this is only about the final prediction part. Yep.
So the algorithm implies post training.
Yes. So yeah, that's the one thing I forgot to mention. So the second one interesting is that the classifier is given as a black box. You only have access of the final output logics. Yes.
I was gonna ask, like, will some similar technique for training help, but since you're saying it's black box, I think.
Yes. So there, we are not pursuing the training-based approach because there are some training-based approach where they try to learn the score functions. The reason is that, nowadays there are so many large models where you don't have access to the training process at all. So I think just for practical purposes, it's much more useful to take this setting.
I mean, in that sense, you don't get the logic as well, right? You only get the final prediction. You don't have the access to the logic as well. The model party.
Oh, so actually, if you take a look at the typical API, let's say on any of the cloud service, typically what they pass to you from the model is the final logics.
Oh.
They don't make a prediction for you, so they pass you the final logics vector.
What if the classes have different risks associated with them?
Oh, yeah, that's an interesting question. Well, in that case, I guess you probably would do a weighting on when you calculate the margin. You probably can do that. You want to account for that. All right. So let me move to the second topic, where I'm going to talk about inverse problems. I think for this audience, probably I don't need to elaborate more on what inverse problems are. You guys probably have seen all kinds of inverse problems over time. So the just my setup is that my measurement y is the object x passed through a physical forward model. F is a forward model that try to model the forward observation process. And the goal is to recover x, of course, inverse problem. So traditionally, we have been, or the community have been using this framework called regularized data fitting. So typically you have two group of terms. One group try to encourage some feasible kind of some agreement with the data measurement, right? And the other kind of term will try to incorporate any prior knowledge about the object, right? Now, deep learning, of course, have changed the landscape dramatically. there are several lines of ideas. I'll just briefly mention them. Some of you have actually done some work there. I heard a lot today, actually. So if you have paired data set, that means you have the object and the observation pairs. You can try to learn the inverse mapping directly. That means the mapping from Y to X. You can just assume a generic neural network architecture, or you can do something more smart. You can maybe actually design inspired first by some numerical method that try to solve this one, right? And one popular kind of idea is called algebraic ruling that's in this family. And sometimes you can also incorporate some generative model because you do have, the data X also, you can train this kind of inverse mapping together with, some modeling of the distribution by X and use that as a regularization term. So this is also very commonly seen. Now, the second line of work is that you only assume you have access to the data set itself, so to the real data itself, not the operations. So for this family of ideas, typically what people do is that they try to model the distribution. Given the data, they try to model the either statistical property of the data set or try to model the geometric property of the data set. But whatever way, you try to kind of model the distribution of the data set in some way. And after that, you plug in this kind of distribution prior into the formulation. So a classical idea in this line is called GAN invariant, where basically you train again on this data set, object on the data set, and then suppose G theta is your generator in the GAN. What you do is that whenever you see the object X, you just replace that by this reparameterization. And your optimization now is about optimizing with respect to the GAN generator seed, the seed of the GAN. And recently, of course, people have played with a lot of diffusion models, and they have tried to generalize this kind of idea to diffusion setting. I'm going to talk more about this later. And surprisingly, there's another family of ideas where I call it a single instance method. Some literature call it a non-trained prior. So this kind of idea is we are taking advantage of the neural network architecture, but there's no actual training data at all. Okay, so it's single instance, or you can call it zero shot if you like. Some people call it zero shot, but this kind of idea is also popular in several domains, actually. You may or may not recognize that. In computer vision, people call this kind of idea deep image prior. And also, there's another name for it, which uses a slightly different kind of representation called the implicit neural representation. That's very, very popular in computer vision for the past few years. And in applied math community, this kind of idea is called physically informed neural network, which is basically the same as this idea, actually. All right, so I'm not going to talk about all the ideas. So if you're interested, you can look at this survey paper, and they are much more comprehensive than what I can do. And also there are a whole lot of recent survey papers that provide a different perspective. But my purpose here today is how to retrain these very flow-based models. By flow-based models, I'm talking about recent diffusion models and also the more general flow matching models. Okay. And last year, there was a very, very comprehensive survey on research in this line. And you can check this one out. Now, I think diffusion model is probably not a new animal here. Okay, so just to remind you, we are talking about the forward process and the reverse process characterized by some SDE, stochastic differential equations. And one quantity that's especially interesting here is this one, right? This one is called a score function. So that's why this kind of learning framework is called a score matching framework. Now, how people actually use diffusion models to solve inverse problems? There are two line of ideas, again, depend on the data availability. So if you have paired data set, you can do supervised learning. But I'm not going to focus on that today. I'm going to focus on the case where you actually don't have paired data set, you only have the object-only data set. Then you probably will do a two-stage thing, where the first stage, you probably will train a different model to try to model the data distribution. And second stage, you try to plug in this kind of data-driven prior into some algorithms, okay? So I'm going to focus on this setting, zero shot setting. So now how people actually approach this problem in general, again, I'm just going to focus on some high-level idea. So one very popular line of thinking is okay, so start with this reverse SDE for diffusion models. Again, the important quantity here is really the swap function. Okay, now when we try to solve inverse problems, we care about both X and Y, right? Because we actually have Y and then we try to estimate X. So it's not only X itself. So then a natural thinking here is let's start thinking about the conditional distribution instead of this one, this unconditional distribution. So I'm going to start thinking about the conditional distribution X provided Y. Okay. And then I can use Bayes' rule because we know this one, we use Bayes' theorem, something divided by something. And then we take the logarithm gradient and after we throw away constant, we get this one. Okay. So now we can plug this conditional distribution back to the SDE, and we end up with two terms now. So one is the original scope function, and the other one is a conditional term, which is tricky to deal with. And many of the papers in the literature on how to use inverse, how to use the different model, prediction different model, solve inverse model is about basically wrestling with this term. How do we use different kind of approximation idea to do this? So again, I'm not going to jump into the technical things, but just keep this in mind that the many methods are actually wrestling with this term, how to deal with, how to approximate this thing, and that actually lead to a family of methods where I call them interleaving method. You can call them other names, but what these methods are doing is this. Okay, so the generation process, the reverse generation process, if you think about it, you can think that as I start from some seed and then I pass through this generation path. And at the end of the day, I generate some image that's on this image manifold. Okay, I generate something that is valid for me. And on the other hand, because we want to make sure we generate something agree with the data measurement, where I call this set a feasibility set. So what this family idea is doing is let's try to, since we have two processes, one process is I do an iterative generation. The other process I do an iterative way of trying to move towards this set. Let's try to interleave these two processes. Okay, so that's why I call it interleaving idea. Of course, the exact formulation, the exact formula may be slightly more complicated than this, but this is just a high level what they are doing. Now, there are a lot of issues with this. Just empirically, you can very easily observe that. And intuitively, you can think of this as, okay, so I want to find the intersection of two sets. And there are two iterative processes. Now, I just combine the two by interleaving the two. There's no guarantee you converge to either of them end of the day, right? Why you believe so? These are two very different iterative processes. So they may not find something that agree with the measurement, which I call the measurement feasibility, or they may not find something that's valid on the image manifold, for example. And sometimes there could be some tricky issue, especially if you have some measurement noise. I'm not going to stress this point. So what we do is we actually come up with some alternative way that's totally different. The alternative way is that we are going to think of the generation process directly just as a mapping. Remember I talked about Gaussian inversion. So Gaussian inversion, we are seeing the generator just as a function. The function just maps from the seed to the image. So we are going to do a similar thing. So we have seed. Our generation process is going to map us to something on the image manifold. So why not just directly plug this into the formulation where I start from my seed, I go through the whole generation process, and then I go through my forward model and I try to seek the agreement with my data variables. Okay. So you can view this as just a generalization of the Guy inversion idea. So nothing surprising here. But the result we get is we at least conceptually, because we do this pass through the whole generation process, we kind of guarantee, find something that's actually meaningful. And also because we are getting a global opposition here, we more likely find something that actually have better agreement with the environment. And that's actually what we found practically. On a lot of evaluations, what we found is that we can do sometimes much better than interleaving ideas, especially on some nonlinear problems. So actually on some of the nonlinear problems, I think, for example, this one, sometimes we can get a PSR point, we can get a 5 or 6 points better than the interleaving ideas. And of course, I think we view on all the metrics uniformly. Okay, so this is a paper that describes the idea, and I don't have much time left. And later on, we actually extend this idea to deal with video restoration, where, of course, video restoration, you have to deal with the whole video sequence. The way we do that, of course, is that we deal with each individual frames, and then we add in a little bit motion information to make sure that the frames are consistent with each other. Now, I want to tell you something very interesting that we worked out recently, is this one. Okay, so nowadays we have a lot of very powerful generative models, right? Stable Diffusion, ChatGPT, what's the image generator? ChatGPT 4.0, right? The image generator, and Google's word is called Imagine 4 or something. But anyway, I forgot all the names, so you can probably see some of the logos here. So we have many powerful image generative models. Now it's very tempting, you start to think about why not use these kind of priors to solve inverse problems, right? Because, these are some of them, especially on open source, we can just download the model, plug in and do that. Okay, we actually did that. And we found something very surprising. So you may think these priors are very powerful, right? Don't you think it's powerful? So what we found is if you are not careful, the performance of this kind of prior, well, it's less than domain specific prior, which is probably not surprising because, it's like you tell me it's a natural image versus you tell me it's a human face image. Well, human face images can definitely provide more information, but the surprising thing is that we found actually it's even worse than the untrained priors. So if you're not careful, actually DIP, which is untrained priors, is doing much better than this kind of priors. And actually, by this point, I have seen 4 or 5 papers published in Europe's ICML that they use this kind of prior to try to solve inverse problem. And they never compare with DIP, of course. But I just want to say, there's a very, very strong baseline that people haven't compared with. And I think the reason is not surprising, actually. Initially I thought it was surprising, but later I think about that. Okay, so these universal generative priors are meant to be general. Basically, just tell you, okay, this thing looks like natural images. Deep image prior also tell you that look like natural images. Why you think one will be stronger than the other one? And in fact, our evaluation suggested deep image priors actually doing even better, actually. But I mean, again, the domain specific one is not surprising. You tell me it's a human face image, versus you tell me it's a natural image, that's very, right? Obviously, tell me it's a human face image is very, very strong. But this begs the question, how do we make best use of these very powerful universal priors, right? we have these readily available, because I think the potential is huge because many image domains probably they have some coverage there, right? But now if they are weaker than even untrained prior, what's the usage of them? At least for solid image from, I mean, of course, they can generate good images, but I'm talking about solid image from. So we made some progress. We haven't fully resolved the issue. We made some progress in our recent paper. It's on tab. You are welcome to check it out. We have some ideas in some restrictive setting. We can get close to domain-specific priors, okay, in terms of performance. But I'm still looking for ideas how to really maximize the potential there. But anyway, I don't think I have more time there, so let me just spend 1 minute on the last topic, which is actually the topic I'm most proud of. it's healthcare. So last 6 years, I will work with many medical doctors. We work on two kinds of work. One is basically, all kind of AI-based diagnosis, prognosis models development, all the nasty data. Another kind of work is I look at the common issues in biomedical research and I try to extract out what are the foundational research we haven't done yet. And this research tends to be the research overlooked by mainstream machine learning research, by the way. So I extract several topics, like, for example, Richard learning. This is not rare nowadays, of course. Imbalanced learning, because there is always imbalance. Selective prediction, I already mentioned that, and so on and so forth. Okay. One thing I want to highlight here is that recently we come up with a new method for dealing with imbalanced data that's especially useful if you have some constraints on some metric, especially when you are going to deal with some indicator functions. All right. So with that, I probably will just end up. Yeah, I would probably just end here, and thanks to all my founders and also all my students. Thank you very much.
How do you do the video restoration? Do you treat every
Yes.
frame equally learn a joint distribution, or you capture the temporal dynamics?
So we are using image priors, so that means we have to deal with a frame by frame.
I see.
But you also need to make sure that across the frames there are some coherent.
Yeah.
Right. So the current idea is that you are going to use some off-the-shelf optic flow estimation modules to estimate the motion, and then use the motion to further refine the quality. But of course, you can see there's a chicken and egg problem, because if your frames are low quality, the optic flow estimation is going to be bad. And so that's a general struggle in this domain, the computer vision domain, that people recently gradually just moved to video-based priors for this problem. But until like early this year, people are still using image priors for individual frames.
So you're optimizing the Z. So
Yes.
you have some correlations.
Yeah, that's a very, very good point. Yes, because across frames, the Z's definitely have some relationship, right? You don't expect the Z to randomly run to other places. Yes, there's indeed some structures there. Yes.
Yeah, be interpreted as some initial noise engineering method. You can see C should just be the initial noise for the Gaussian.
Right.
And then treating models as one, usually treating models as one R, right? So it's like a iterative sampling composed together comes overall sampling map, and overall sample results for your models.
Right. So the R here is the whole reverse generation process.
Yeah.
Yes.
Yeah, but like sometimes this process is stochastic, and the final generation is like
right, that's a good point. So we typically only take the ODE based flow.
Yeah.
Yes. Yep.
You just mentioned briefly, applications to healthcare and probably work on imbalance data.
Yes,
and
yes,
precision recall. If you're trying to, say, optimize precision for a given recall, do you solve that using the method you talked about to begin the talk, because that would be a non.
Oh, you mean a solver?
Yeah, the non-convex.
Yes, we have tried that. That's giving us reasonable results for small scale data, but we are also trying to develop another more scalable solver. Hopefully, we are going to incorporate that into the NCVX package in the future. So we are developing some stochastic solvers to be scalable. So as I mentioned, the current limitation of NCVX, the package ransom solver is fully deterministic. You can deal with up to several million variables, but no more than that. Yep.
That's the part regarding the first part.
Yep, yep.
Trying to grasp the key message, like you said about like the drawback of previous methods on this probability to decide whether to stay or not, and versus your method which directly operate on logics. So it's the key message is that we shall not pass through softmax for this task.
Kind of, yes, kind of. So the tricky issue is okay, so there's a lot of research called calibration. This is especially in statistics, some research has pursued this. So that basically means how do you align this kind of confidence with human perception of confidence? Okay, so that's one line of work. It's called calibration. Now, what we found is no matter the calibration, the problem with the current confidence scores, when you apply them to the downstream selective classification, is that they are very, very sensitive to scaling. Actually, scaling is just one of them. So what do I mean by scaling? So imagine that you have prediction before you pass through the softmax, you have the raw logits, right? So if I multiply the raw logit by a constant, that's not going to change the ordering, right? But that's going to change the gap between the softmax logits, and that have dramatic impact on the performance of selective classification. Okay, so but actually in calibration literature, that's one way that people are doing calibration. But anyway, so I think the high level message is that if your end goal is to do selective classification, you probably don't need to worry about calibration because calibration doesn't change the ordering, and selective classification actually only has to do with the ordering. So you can skip the calibration step. And it seems like currently this margin-based metric, margin-based score function is a much more reliable choice than the previous ones that people are using.
Any more question? If not, let's thanks Ju for the wonderful talk.
Thank you, guys.